Hello, everybody. Welcome to another installment of our daily lives, where students can kind of jump on and ask any questions that they want. If you have any questions, feel free to drop them in the chat. Otherwise, I'll just continue with kind of what we were going through yesterday. So basically, what we talked about yesterday. Let me actually share my screen first. What we were talking about yesterday was how to use the Riemann sum, right? This idea of we have this exact area under the curve that we want to find, and we can approximate it. I don't know why it's not. It doesn't seems like it's not completely loading. There we go. So yeah, we want this. We want to find the area under this curve. So this kind of unusual curved shape. We want to find the area under that. So the way we do that is we approximate it with the areas of rectangles. And again, we have a couple different ways to do that with the right Riemann sum, the left Riemann sum, the midpoint rule, etc. And basically, we went through some examples of using the formulas that we've been talking about this week. We put actual numbers to them and we came up with actual calculations. So, like for the right Riemann sum, for example, 11.125. For the left Riemann sum, 12.625. For the midpoint rule, whatever that is, I forget, like something close to that. So, also a number that's slightly different, but also pretty close to those when you simplify it. That's all well and good, but the big elephant in the room here is that we've been talking about approximations, not the actual area under the curve, right? So it's like it's not exactly correct. It's an approximation at best. What we're going to do today is we're going to do a slightly different problem. What we're not going to find this answer. We're not going to approximate the answer. We are going to find the exact area under the curve now. So we're going to find, we're going to find we're not going to say approximate the area. We're going to say find the exact area under the curve f of x between x equals -1 and 2. So that is what we're going to do now. And we'll talk. There's a very interesting connection to what we did last time. So what we did last time is not useless. In fact, we're kind of building off what we did last time, but there's something very clever we can do. So to start off, let me actually open up kind of what we did last time. So let me set us up. So remember, with the function we're talking about here is 5 minus x squared. We're going between -1 and 2. And last time, if you remember, we actually used 6 rectangles. So 6 rectangles. And again, with the left Riemann sum, we got 12.625. With the right Riemann sum, we got 11.125. The midpoint, apparently, we got 12.0625. So we get 3 different approximations, and you can kind of see how the rectangles are shifting. We're trying to get the same area every time, but right, like the way we choose the rectangles, the way we choose the height of the rectangles does affect the output a little bit. So that's why we're getting slightly different answers here. They're all very close to each other, as you can see, but they are slightly different, right? Depending on whether you use the left, midpoint, or the right. So that's kind of the idea. Now, again, this is obviously, as you can see, as we already mentioned, an approximation, right? Because the like what's in green is not the true area under the curve, right? We can see little gaps here where we're like kind of undershooting and overshooting. So the question is, here's $1,000,000 question. Is there anything we can do to make our approximation better? And the answer is yes. There's one very simple thing, simple to understand, but maybe a little bit more work to do to make it better. I'll give you a second. Feel free to just drop it in the chat if you have any ideas. But yeah, so I'll say basically have more rectangles. That's the short answer. So right now we have 6 rectangles. If I have, say, 12 rectangles, again, it's still pretty much the same, but there is a slight improvement. So here, and the other thing is between these 3 values, you can kind of see they're getting closer now, right? It's like it was like 11.25, now it's 11.59. It's coming up to the 12, which was about what the other ones were, and this one was like 12.625, I think. Now it's like coming down towards the center, so we're getting kind of closer to 12. It looks like. So that's good. So if we double the amount of rectangles, and again, you can kind of visualize this. I can even have fewer rectangles, right? So obviously that's like way off, right? Like maybe we're overestimating the area by this amount, like this chunk. Like maybe this green, like you can kind of imagine there's a chunk of this green area right here that you can kind of fill in here. and that would kind of be correct. But all this other stuff down here is overshooting it. So this is overshooting by a lot. But as I crank up the number of rectangles to like 12 or 16 or whatever, pretty good. And now, if you're kind of looking at this, you should have the kind of your next natural question is, why don't we just keep going, right? If it gets better when we go from 6 to 12 or 12 to 20, what if we just take it to the extreme? What if we just go to 100 or a million or I'll say it like this, 1,000? When I go, and again, to be clear, it looks like right now we're dealing with the true area under the curve. And this is the other thing, by the way. If we really do have 1,000 rectangles in a width of 3, so think about it. The width of each rectangle is extremely small. It's like 3 divided by 1,000, 3,000. So it's an extremely small width, but you can still do it. It's not 0, and that's the key. As long as it's greater than 0, you can do that. And here's the other thing: you see how, as I change from the left to midpoint to Riemann sum or to right, you see how it's all barely moving at all. Like it's all getting really close to 12, basically. Like all these numbers are really close to 12. They are changing when I change between these, but it looks like it's not budging. So you might think this is actually the true area under the curve if I use 1,000 rectangles, but it's actually not. If I zoom in far enough, we're still talking about rectangles here, right? And if I change from left to midpoint to right Riemann sum, like you can see the rectangles changing, and that's what's responsible for the changing sum of that total green area. But it doesn't change by much, I guess is the point. So this is kind of the key idea. The key idea is if you want to, again, we can approximate the area under the curve with just a few rectangles, but if you want to make it really good, just let it keep growing. Let the number of rectangles keep growing, and the area will get better and better, or the approximation will get better and better. And there's no limit to this, by the way, right? Well, depending on what you mean by limit, there is. So there's no upper limit to the amount of rectangles you can have. You could have 100 or 10,000, 100,000, a million, until you eventually break the calculator. And then like here, it's not exactly 12. It's like 12.0000 something, but it's like so close to 12 that the calculator can't represent the difference. So you can just let the number of rectangles like blow up to a gigantic number, like a billion, for example, here. And again, you keep going. A billion is puny compared to infinity. Basically, we can take the limit as n goes to infinity. We can let n approach infinity in the limit. And then, now to be clear, this number down here, like what we actually get from adding up all these rectangles, it will never perfectly equal 12. It looks like it does. Like even right here, here's a good example. It's like we're plugging in n equals a billion. It's still not 12. It's 11.9999999, however many nines you need. And so it's not quite 12. But here's the key. This number is going to get, we can tell just by looking at it, right? We can tell by looking at it. It basically is getting infinitely close to 12. Right. So the one in the middle, that's like really close to 12. The midpoint, the left is like very, very slightly above it. The right Riemann sum is very, very slightly below it, 11.99. So it's like no matter which approximation you use, they're all obviously approaching 12. Again, that's where the word approach comes in. We've talked about that before. In calculus, remember, calculus is the study of limits at the end of the day. So calculus is the study of limits, meaning it's kind of a weird idea, but in calculus, we don't talk about what the thing actually is. We talk about what it actually gets closer and closer to equaling in the limit. And we can talk about the thing that it gets close to, even though it might never hit it. And this is a good example of that. So just like with derivatives, you like let delta x shrink to 0 and you see what the slope gets really close to, but never quite hits. Here, we're using this trick to find the area under a curve. We're basically adding up the area of a bunch of rectangles, which is a Riemann sum, but we're letting the number of rectangles blow up towards infinity, and then our sum will in the meantime approach some number, and we can talk about what that number is. That number is the true area under the curve, even if we'll never quite get there with this technique. We can like obviously approach it in the limit. So that's kind of complex, but hopefully that makes sense. So I guess what am I getting at here? If we're trying to find the exact area under the curve here, we want to use actually the same exact techniques we used before. So if I go to yesterday, remember we talked about a lot of this stuff here, right? So we're still using this idea and we're still using this key formula. The difference is n is no longer 6. N is now a limit that will approach infinity. So if I bring this over here, the way we're actually going to do this is Remember, delta x is that. We're going to make one tiny adjustment. Again, this is the same formula that we used yesterday. It was just, we're using summation notation. The only thing that changes now is we do the limit as n approaches infinity on the outside. That's it. That's the only difference. And again, it's kind of a big change. You'll see it's like a lot harder to calculate that, but the benefit is it gives you the exact answer. So this is what we're doing. Now, the question is, how do we actually calculate this? So like hopefully the visual that we just showed that like shows the idea. It's that you have the area under the curve, which the calculator is calculating that automatically, and then you just keep cranking that up forever, and then see what that number gets closer and closer to forever. That's what we're doing. Now, how do we actually do it? Now, obviously, we can't literally just add up an infinite number of things. So let's just point that out, right? When we were doing this approximation yesterday, we could actually, because we only had 6 of them. We didn't have an infinite. Even if we had a million or a trillion, in principle, you wouldn't want to by hand, obviously. You would need a calculator to do that. But in principle, you can do it, is the point. Like if you have a finite number of them. If you have an infinite number of them, you can't even add them all up in principle. So that's kind of tricky. So it's not going to be as simple as what we did yesterday. Not that yesterday was simple; it's just simple compared to what we're going to do today. It gets very complex. But instead of basically, instead of just adding up the heights the way we did yesterday, we're going to need to systematize and formulatize things a little bit more and kind of hope that things pan out. So here, let me give some examples of this. For this, let me say that, and actually, let me back up a bit. So here, if you think about it, we have to find what here's what I'll say. We have to find what, how should I word it? We have to find what like first off, we have to find one way to do a sample point. I'll say that. And remember, we could do three different techniques that we kind of talked about. We do the right Riemann sum, the midpoint, the left Riemann sum. We talked about all of those. And again, you can choose whichever one you want. We just show that they're all going to approach the same value in the limit. So the question is, which one should you use? Because we are going to need it. Like, remember last time I mentioned, I actually recommend against using the formula when you're just doing the approximations. I would prefer, it's better to just visualize and common sense your way through, in my opinion. Well, here we actually need the formula because we can't draw it now. Basically, we can't draw all the rectangles, so we can't exactly common sense our way through it anymore. Because like as the number of rectangles approaches infinity, delta x is going to approach 0. That's kind of another like the width of each individual rectangle has to approach 0. We're trying to squeeze more and more rectangles in the same finite space. That's basically the idea. So here we are going to need these formulas or one of them at least. So the question is which one? So this is the formula for the right Riemann sum. This is the formula, or if I can find it, or where is it? Oh yeah, never mind. Let me go up to the top. Yeah. So this is the formula for the right Riemann sum. This is the formula for the left Riemann sum. This is the formula for the midpoint. You can use whichever one you want. But we talked about this yesterday. Obviously, there's the simplest one right here. This is the simplest one, the right Riemann sum. So just, because we like making our lives simple, they're already complicated enough as is. Let's just use that. So let's just use the simplest formula that we can. And if I do that, let me copy this down. What we're doing now is we're basically going to take, f of basically a plus k times delta x. And by the way, we should actually calculate what delta x is now. For this problem, remember the way we did it last time, we did the total width divided by the number of rectangles. Here, the problem is we don't have a number of rectangles. We're going to let it approach infinity in the limit. So what you actually need to do is just leave the n, but you use the same formula we used yesterday. So here it'll be, hopefully it's clear. 2, b is 2, a is -1, 2 minus -1, 2 plus 1, 3. So delta x is 3 over n. And if I pop that in, you can kind of see where that comes in. So here, actually, yeah, I'll do one thing at a time here because this can get overwhelming very easily. So the delta x is 3 over n. So 3 over n times k. Cool. And then we have this. So there you go. And again, one more step. Remember that we haven't incorporated the function we're actually talking about. What is that? 5 minus x squared. So if f of x is 5 minus x squared, what we're trying to find here is f of, and actually I should, actually before doing that, sorry, I should, let me do this slightly differently. Let's also do the a value, right? A is -1 plus 3 over n times k. So here, if f of x we know is 5 minus x squared, then what is f of parentheses -1 plus 3 over nk? Remember, that is the special formula that we use to automatically find the right Riemann sum. Again, we need to use some formula to systematize it because we can't possibly count out each one. There's an infinite number of them. So we need some formula to systematize it so that it automatically pops out basically every time. So the question is, what would that be? Well, the trick here, because this is essentially what we need to figure out now, right? If you want to compare these, basically the way to think about it is that we just have a new input. So, right, we used to have an input of just x. That's kind of like our placeholder. Now we have an input of this whole thing. So, what's the rule? Basically, wherever you see x in the original, you just replace it with. So you just replace it with this entire thing in here, which is a whole other formula, but in parentheses. So hopefully it's clear. You get 5 minus parentheses, -1 plus 3 over n, or -1 plus 3 over n k, the whole thing squared. Hopefully it's clear that that's what the formula would be. Basically, wherever you see x, I just replaced it with that. So that's what we're going to do here. So when we take that into account, I'll just pop that in where the old formula was. And then now we're trying to do this. And then the whole thing, by the way, times the delta x, or the 3 over n on the outside. Now this is getting crazy, right? So these are hard. Like this is I would say this, what we're doing right now, is the hardest topic in AB at least. BC has, I think, some harder topics maybe, but this gives them a run for their money. This is called the limit definite. We're like using the limit definition of the integral, by the way. And I know I don't think I've brought up integral. We're just talking about area under the curve. We'll talk about what it means probably tomorrow. Um, but yeah, the next question is, how do we actually solve this thing? It looks like it's going to be very painful, and it is. I probably should have chosen an easier function to work with, to be honest. Um, but anyway, we'll give it our best shot here. So looking at this, and one thing that's probably, or one thing that's probably good to do to start, just right off the bat, is to basically think about how 3 over n, like every single term is going to be multiplied by 3 over n. And this is where it gets a little confusing, because n is, how should I say it? N is basically, and it affects the limit, right? Because obviously, like, or n changes in the limit, but n does not change in the summation. So, and this is kind of a weird way to think about this, right? Like we can't literally add up an infinite number of things. That's kind of the problem. So another way of looking at this is what we're really going to try to do is we're going to try to find a formula that represents this whole thing. Like if I have n terms and I add them together, we want a special formula that equals that thing that basically is a function of n. And then once we get that formula and we can prove that, oh, that is, like, if I have n rectangles, that's what the formula would be. Then you just take that expression and then take the limit as n approaches infinity, and we should be able to see it just kind of like you did early in the year when you were dealing with horizontal asymptotes or limits at infinity. It's kind of the same idea today. So that's what we're really doing. Um, so that's kind of our main goal. And when you think of it like that, and you have to think, like, for the summation, you have to think of n as a constant. We're leaving it as a variable so that we can take the limit of it later, but for the summation, at least, it is a constant, which means you can factor out, because n is a constant. This is a constant in each term. So, like, this, you have each term that changes. Why does it change? Because it has a k in it, right? K changes for each term, but the 3 over n part does not have a k in it. So it's actually a constant with respect to the terms. It doesn't change. So what you can do is you can just kind of factor it out. So you can't factor it outside of the limit, to be clear, but you can factor it out of the summation, and that will probably make things a lot easier to understand. They're already complicated enough, as I'm sure you noticed. And then what we can do, and actually I'm going to tweak this. I'll say 3k over n, just a slight change. Um, yeah, and then that whole thing squared, like that. So that's kind of one thing you can do right off the bat. You can just factor out the delta x out of the summation, not out of the limit. And again, I know this is super abstract. So what I'll try to do just to show this, like let's actually talk about what we're actually doing here. So we're doing the limit as n goes to infinity, just to understand the trick we're pulling here, because it is kind of abstract. What we're doing is, well, what would the first term be? If k is equal to 1, does it make sense? This first term would be basically 5 minus -1 plus 3 over n squared, whatever that is, times 3 over n. That would be the first term. And then what would the second term be? Well, now everything's literally the exact same. So plus everything is the exact same, except now k is equal to 2. So now it'll be parentheses 5 minus parentheses again, -1 plus, it won't be 3 over n anymore. It'll be 3 times 2 over n. So 6 over n squared, whatever that is, times 3 over n. And then you like basically it's going to be the same term every time, except only that's going to change. Basically, it's going to be 3, 6, 9, the way we're systematizing it. But the thing I want to point out is, again, if you look at just the plus signs here, so that's one plus sign, that's another plus sign. These are the terms. The only thing that changes each time is this 3. That should be 3 over n, 6 over n, 9 over n, and it'll continue like that. But the thing that we just did, remember, we have this. Like every single term is going to be multiplied by 3 over n. We can just factor that out. That's what we did here. That's the equivalent of what we did. We're basically just, if you want to visualize it, and I'll try to do this for each step, just because I know this is very complex to follow. But we just pulled out the 3 over n, and now we're going to be left with what's left, basically 5 minus -1 plus 3 over n squared plus. So we're just factoring out the 3 over n. That's what that property allows us to do. Hopefully that makes sense. Plus 6 over n squared plus dot dot dot. Cool. So that's that. Now what? So like I said, that's that. Now back to kind of our normal process here. What we can do is we want to basically work our way down and simplify as much as we can. So I'm going to keep that the same, and now I'm going to try to simplify this. So what would -1 plus 3k over n, the whole thing squared, equal? Think of it like foiling. It is foiling. We're foiling this thing. So that times itself. Well, -1 times -1 is +1, right? And then what? -2 times 3k, so 6k over n, right? So if you're just imagine it like this, you have -1 plus 3k over n times -1 plus 3k over n. So -1 times -1 is +1. Then -3kn plus -3kn, or plus -3kn, -6kn. And then here we multiply these, that'll be what? Plus 9k squared over n squared. There you go. Hopefully that makes sense when we expand it. And now, and again, what is this? I'll try to do it for most steps, but I think you get this. We're really just, all we did is like we kept this the same, but we're just factoring each of these, or not factoring, multiplying out. That's all. And then now this gets a little more interesting. So here, if you think of this, here's the next trick, right? We're constantly pulling tricks here. So let me do this. And I'll get rid of the n, or we'll just send it back to the normal color. Limit as n goes to infinity. And then here, what are we going to do? So this is the next trick that we're going to pull. So we're going to break these up. So instead of having the summation of this whole crazy, and actually, let me do one more thing before I go there. Let me just, what I would do first is distribute the negative sign. And actually, yeah, 5 minus 1, hopefully it's clear, that'll just be 4. And then plus 6k over n, 6k over n minus 9k squared over n squared, like that. So if I just distribute the n, or distribute the negative to each of these, and then combine them. Hopefully that makes sense. Now, what do we do here? So basically, the trick we're going to pull now is we're going to break apart the summation. So again, with each property, what we're really learning kind of is summation properties. We'll learn why they're true, but for now, actually, let's do this. So k equals 1. And that's why I'm doing the thing I'm doing to the right-hand side, but I'm just going to say that. That's the first thing that we're breaking up. And then basically the way you can look at it, it kind of looks like you're distributing the summation to every term. That's kind of what it looks like, but it's not exactly what's happening. We'll talk about that in a second. So here, again, if I just do this summation, I'll just say we're distributing the summation to every term, even though that's not the right terminology. It's what it looks like. So 6k over n. And then what else do we have? We have minus, minus the summation from k equals 1 to n, 9k squared over n squared, like that. Cool. So hopefully that makes sense. Or actually, it probably should not make sense yet. What we can do, though, is this is essentially what's being done. So here, once we're at this point, we basically have limit as n goes to infinity of 3 over n. And then we basically have, if you expand this, this would be what? 5 minus, and then it would basically be this formula, right? So it's like 5 minus, and then you'd have 1 minus 6 over n. So like this first term is k equals 1, and then you have plus 9 over n squared, right? And you can see how that lines up with, like, if k is 1, that's what this is supposed to be when k is 1. This is supposed to be when k is 2, etc. So when we line it up, yeah, we get that. And then for the second term, we get, so that's the first term. And then for the second term, we get, 5 minus parentheses 1 minus 12n, right? Plus, I guess, or let me pull this over. So it won't be, 9 times k squared. So, or another way you can think about it is, I guess, 6n squared, which is 36. So 36 over n squared. And then you could keep going like that. And then if you were to simplify it, so you'd have, basically for this first one, you'd have 4 minus 6 over n plus 9 over n squared plus 4 minus 12 over n plus 36. Or sorry, minus, or that should be plus, that should be minus. And yeah, sorry, that should be plus. That should be minus. And it should be fitting the same formula, like no matter how you do it, as long as we're doing everything correctly. So that's kind of what we're talking about now. And now, why is this valid? Why am I allowed to do what looks like distributing the summation symbol? It's not what's actually happening. But the reason you're allowed to do that, again, I'm not gonna rewrite the limit every time. But basically, the reason you can do that is, what if we just put all the fours together? What if you just, because again, what we're really doing behind the scenes, the reason this really works is the commutative property of addition, right? 3 plus 2 is the same thing as 2 plus 3. So if you have a bunch of stuff added together, it's still the same thing if you change the order. That's essentially what we're doing. So instead, like, we're trying to put like terms together, basically. So instead of putting 4 plus this thing plus minus that thing, 4 plus this thing minus that thing, and it gets a little crazy, what we can just do instead is, what if we just put all the fours right next to each other? There's going to be n fours. So what if we just do 4 plus dot dot dot, and there's n of these. So there's n of these. That's what this first term represents. Like k equals 1 to n, 4, that's 4 plus 4 plus 4 plus 4 dot 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 n times. That's what that means. And then you could just group the second ones together, right? So it'd be like 6 over n plus 12 over n plus, you could probably guess the next term. It looks like it'll be maybe 16 over n, or sorry, 18 over n. But we don't really have to worry about that yet. But that's what happens when you group all the middle terms. That's this. So when k equals 1, that's 6 over n. That's the first term. Plus k equals 2, 12 over n. K equals 3, count up. Remember the summation notation? Very right. Again, you don't have to do any of this stuff on the right-hand side, to be clear. I'm just doing that to make it, like, make sense what we're actually doing. That's all. Like, you can do this whole problem with what we're doing on the left. It's just as long as you know the rules. I'm just explaining why the rules are the way they are at each step. And then this next one, again, every term here, like negative, negative, we're gonna have like every term is gonna be negative, which is why we can, which is why I pulled this negative sign out here. I really did another property. I probably should have waited to do that, but I did it already, so I'll just list it like that. And then think about what this is gonna be. Well, the first term is 9, so 9n squared plus 36 n squared plus, and then you can do, you can keep going like that. Doesn't that fit what we have here, right? When k is equal to 1, yeah, it is 9 over n squared. When k is equal to 2, 9 times 2 squared, 9 times 4, 36, 36 over n squared. That works. So this is the trick. The reason we can do what looks like distributing the summation is because we're really just doing the commutative property of addition. We're really just rearranging. It's kind of weird because we have an infinite number of terms, or at least we have n terms, but we can systematically rearrange it to put all the similar ones that go together in a similar pattern next to each other. That's good. Now we finally, let me zoom in. We're finally getting to the point where we have to evaluate this. So now it's like we're getting to the point where it's now time to zoom in a bit, to evaluate these. So here, see if this makes sense. What is 4 plus 4 plus 4 plus 4? Keep doing that n times. That is, hopefully it makes sense. That is by definition 4 times n. That's what it means to like multiplication is repeated addition. So like think about it. If n is 10, if you had 4 plus 4 plus 4 plus 4 plus 4, or actually let's do 5 just for simplicity. Let's actually add 4 to itself 5 times. Assume n is 5. 4 plus 4 is 8, plus 4 again is 12, plus 4 again is 16, plus 4 again is 20. That's what 4 times 5 means. Multiplication is literally repeated addition. So that's good. Now for this next one, we can't, so that one we can just solve right off of that. This next one, we can't solve it right now, but there is something we can do. So here, I'll say this, and actually, I'll do this. See if you can figure out what this next one is. I'm actually going to pause the video here. Or actually, no, I think I'll go a little bit longer. Does everybody want? I think everybody, yeah, as long as people still want to go on. So I'll say maybe a little bit longer today. So with these, basically, so this one's, here's what I'll say. This is the second one is trickier to solve. So what's 6 because it's not a constant anymore, right? It's not like just the same thing times itself anymore. It's like now the thing that we add changes. That adds a layer of complexity to it. So let me try this just to simplify. What you can do is remember n is a constant with respect to the summation, and you can factor out constants. So for example, you can do 6 over n times the summation from k equals 1 to n of just k now. See if that makes sense. So here, what did we actually do? So again, this is going to be 6 over n plus 12 over n plus 18 over n. What we really did is we just factored out 6 over n out of all of those, and we just had what? 1 plus 2 plus 3. Doesn't that make sense? Plus dot, dot, dot. Instead of 6 over n plus 12 over n plus 18 over n plus 24 over n, just factor out 6 over n out of everything. That's this, factoring a constant out. So again, this is the reason this works. The reason you can do this is because of the distributive property. Now, to be clear, you cannot factor out the k. So you can't pull the k out because the k changes inside of that, like for every term. You can only pull out constants. You can only pull out things that do not change. Things that do change need to be left in the formula. But hopefully that's clear. So we've simplified what we now need to figure out, at least. We've simplified that down a bit. And you can do something similar here. You can do minus 9 over n squared. And then you can do the summation from k equals 1 to n of, now the difference is k squared. And again, doesn't that kind of make sense if I go over here? So if I go over here, that should be minus 9 over n squared, and then we'll be left with what? K squared. That's 1 plus 4 plus 9, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, plus dot, 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 and you just do that forever. So hopefully that makes sense. Again, we're just, at every single step here, we're really just using properties. Now here, So that's good. So we've solved the first one, right? And this is the hardest part of this, by the way, just to be clear. Like actually solving the summation, like, or in this case, we have multiple summations. That's the hardest part. We've already done. We have three spots where we need to do it. Here, we've done it in one. Now here's my next question. What is the summation of? And I think yeah, let's go a little bit longer. I don't think we'll be able to fully finish this. This is going to be probably we'll pick up with this one tomorrow because this is actually pretty involved. But you can see why we're going to do this process once. Let me put it that way, just to show you that it works. But you definitely don't want to do this process. Look how painful it is. The good news is we're going to be able to find a we're going to talk probably not tomorrow, but probably the day after. We're going to talk about a way that's way simpler than this method that allows us to basically do it with a lot less pain. But again, we're just taking that idea, the same formula, and we're just letting n go to infinity. That's the only change we made. Now to actually evaluate, you can see how painful it is to do that, but we can do it, and we will finish with this one probably tomorrow. But hopefully it's making sense so far, because this is, like I said, this is like the hardest thing in an AB by far. It's almost as hard as the BC topics, some of the hardest ones. It's harder than some BC topics, I'd say. But anyway, what do we do with this? So here's what I'll say. This part is not obvious, but this is what we'll wrap up today with. What I'm claiming, remember, we have 6 over n, which is just some constant. What is k? So the summation from k equals 1 to n of k. That is our question. And again, we'll have to deal with it for k squared in a second. But for now, just for k, what is it? So think about what that means. It means it's basically 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. So, and that's what we have here on the right too, by the way. 1 plus 2 plus 3, and you just keep going. When do you stop? When you hit n. What is n? A variable. So we need to turn that into a formula, basically. That's our goal. Now, here's my claim. My claim is that equals n divided by 2 times n plus 1 for any n. So if you're starting at k equals 1 and you're just counting up by 1 every time, and you go until n, whatever n is, that will always equal n over 2 times n plus 1. How do I know that? Let's talk about it. So there's a special story here. First off, so actually I'll start off with a story because I do think it's kind of interesting. Let me come down here because I don't want to go to the right. I think, well, actually, I think the right, like the stuff that's written on the right, I think has kind of served its purpose at this point. Like, because like as long as you get what we were doing with the summation every time, I think that's the most important. So yeah, now I am going to. I'll just do it right here. So if you want to search somebody online, I recommend checking this person out. I'll just say Gauss. Yes, this guy. So German mathematician who lived in the 1800s. I actually was born in the late 1700s. I didn't know that. I didn't know he's that old. But anyway, this guy is one of the. I don't know. There's a lot of competition, but he's definitely one of the smartest guys to ever live. He's probably top 30, I'd say, or top 20, maybe even. But basically, this story again, I might be getting it obviously it's not on video because it was in the 1700s when this happened, but the story goes like this. Basically, when he was a kid, he was a German kid in kindergarten, and basically the teacher wanted to be lazy. His teacher wanted to be lazy, so the teacher wanted to just give the students busy work in class to keep the students busy for like 2 hours so that the teacher could just take a break and like not have to do anything. So what did the teacher do? And again, like I said, I don't know the story because like it's kind of like a game of telephone of the centuries. Like who knows if the story's exactly right, but something like this definitely happened because he invented this formula that I'm about to show you when he was like 5 years old. So he came up with this idea, and honestly, I wouldn't be surprised if it's on the page. Let me see here. Yeah, he was a child prodigy, so you got to be a child prodigy to come up with this formula we're about to figure out. Yeah, I don't know. So yeah, his teachers noticed. Yeah, I don't know. You can check this. Okay, here it is. This is it actually. An apocryphal story, meaning we're not sure if it's true. It might be wrong, but yeah, teacher, sum the numbers from 1 to 100. Yeah. So I'm at yeah. So like again, it's like it might be like the details exaggerated, but this is the story as I've heard it. I'll say the teacher wanted to like basically keep them busy. So he basically said, here was the assignment. Hey, add the number all numbers from 1 to 100. So 1 plus 2 plus 3 plus 4. Again, this is a group of kindergartners, like 5 or 6 year olds, and the teacher says, just like add those up and let me know when you figure out the answer. And again, this is obviously before calculators. This is the 1700s we're talking about. So today it would be pretty fast. You could do it relatively quickly. Back then, it would take a while to add up all those numbers. So that was the assignment, and the teacher was kind of expecting, like, oh, I can just take it easy for 2 hours. I can just take a break, basically. And then what happened is basically Gauss figured it out in like a minute as opposed to like 2 hours. So it would have taken 2 hours to do by hand. Gauss came up with the answer um, in like a minute, because he didn't actually add it. He actually figured out a clever formula. And basically, the teacher got mad at him for a couple of reasons. One, that he ruined the teacher's break, right? The teacher was trying to give them busy work so that he could just take a break. And so Gauss basically robbed 2 hours of his break. So that's why he was mad. He was mad when Gauss came up with the answer so fast as a student. And the other reason is because he thought Gauss cheated. Like the teacher didn't believe that Gauss actually figured out the formula um, until Gauss explained it to him. And like he got to know him more. Then he started to, I was like, oh, wait, no, this kid's actually just a genius. He did actually figure out the formula. So, what is the formula? What's the idea? So, here's the idea. We have 1 plus 2 plus 3 plus dot, dot, dot. Actually, I'll do it a couple more since we have around plus 4 plus dot, dot, dot plus what? 97 plus 98 plus 99 plus 100. Now, you can sit here and try to add up all these numbers, but that'll obviously take a while. And you can do it like if you have like 4 or 5 numbers, it's faster to just do that, obviously. But if you have 100 or 1,000 or a million or a trillion, good luck. You don't want to do that. So this is where Gauss's formula comes in handy. So what did Gauss realize? He didn't want to. He knew it was going to be a pain to have to do all this stuff. So this was his ingenious insight. He's like, what if I just pair the first number and the last number? So 1 plus 100 is what? 101. And then I pair the the second number with the second last number. What is 2 plus 99? Also 101. Because once you do that, basically every time you're adding one to this and subtracting one from that. So it's like they always add up to the same thing. So 3 plus 98 is, you guessed it, also 101. And then you just do that. And then the question is how much. So basically you can look at it as a bunch of pairs of numbers that are, or basically, or actually, I don't want to get ahead of myself. So how many times can you do that? Well, basically until you have 50. So you have 50 pairs. So if you think about it, you have 50 pairs of 101. So to summarize, you have basically this right here. So the 101, think about it like this to generalize the formula, because it works with any n. It doesn't just work with 100. 101 in the formula, that's like the n plus 1. So we have the 1 at the front, and the last number is n. So that's like the n plus 1 in this formula. That's the 101 here. It's like you just add the first number, which is 1, and then you add the last number, which we're saying is n. And then how many pairs do you have? The 50 is like the n over 2 in the formula. So you have 50 pairs of 101. So 101 plus itself 50 times, or 101 times 50. Like remember, the definition of multiplication is repeated addition. There you go. Hopefully that makes sense. This is the genius formula. So this works with any n. If you want to add 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, you can do it with that formula. And it's not that complicated, right? It's like it's just as easy to add the first 100 numbers as it is to add the first 1,000 or first million numbers. It's not that much more difficult, honestly. Which is kind of crazy, right? Because like if you did it the old way, it would be like 10 times, 100 times, 1,000 times harder, like 1,000 times as much effort to like manually add it by hand. But with this formula, you can get it done and no problem. So hopefully that makes sense. And now I'll just say this. Actually, I'll go like this. So here, this formula is kind of, so we have the -9 over n squared. I might as well just finish off today because I know we're already making progress. So what is the this formula? There's something similar. I'll say there's a similar formula. Um, let me grab it real quick. So, or let's see, I'm looking, here we go. This is what I'm looking for. So here, there were like once this was discovered, basically they came up with a bunch of other variations of it as well. Those are a lot more complicated. I won't get into those, but basically I'll just leave this table here. So in terms of this table, you can see here that basically what we just did is this, right? We just did like the summation from k, and that's that formula we use, n over 2 times n plus 1. For k squared, according to this table, it's n times n plus 1 times 2n plus 1 over 6. Why is that formula that way? I'm not going to get into it because it's a lot more complicated than the one we just did, but it's a similar kind of idea. It's a similar kind of proof, but it's far more complex. But it's the same process. It's like you actually write 1 squared plus 2 squared plus 3 squared plus 4 squared dot 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 all the way up to 100 squared, and then you find clever ways to rearrange it and basically add it. So that's why that works. So hopefully that part makes sense. But again, no, I'm not going to show the proof to that one, but I'll just use the formula. So basically, whenever you have summation of like k equals, or summation from k squared, whatever, you need to know one of these formulas. And there's a bunch of different formulas to know, by the way. So there you go. Hopefully that makes sense. Now what we're going to do, well, actually think about what we've done so far. We've gotten rid of the summations. That was the hard part, working with those summations. That's why integrals are so much harder. What we're doing now is really getting into integrals. We'll see that later. But integrals are so much harder than derivatives because of that, because they involve these summations. So being able to get rid of those is really important, which is what we just did. So now, how do we actually solve this problem from here? Here, now we actually have a problem that we can solve. So looking at this, so this is kind of interesting. I'll try to simplify it as much as we can on the inside. So we still have this, limit 3n. Because remember, what we said is we started off with a pretty crazy formula, right? With basically this formula. What we've done at this point is we found a way to turn this entire thing into like not having a summation. We found a way to systematically, piece by piece, reason our way through it and like use formulas where necessary to simplify certain summations to basically get just a function of n, a formula with just n in it. And now that we have that, now we can just like basically do the normal limit as n goes to infinity or limit as x goes to infinity. This is like a horizontal asymptote that you did earlier in the year. It's kind of like that. So now we're going to use those same rules. So here, I'll just leave that. That's 4n. Then this thing I'll say 6 over 2. So it's actually going to be 3, and then the n's cancel out. So hopefully it's clear that if I simplify this, it'll be 3 times. Actually, I'll say 3n plus 3, right? 3 times n plus 1, and then I factor that or multiply that in. Cool. And then here we divide by that. So we get what? Minus 3 over 2n squared. And then this is what gets a little trickier. I kind of don't want to factor this out. I guess I can. Actually, I'll simplify one of the ends. One of the ends cancels out, so I'll leave that. And then here, what will we be left with? N plus 1 times 2n plus 1, right? What will that be? That'll just be that'll just be n 2n squared. So if we just multiply that through 2n squared plus 3n plus 1. So there you go. In the end, we could multiply on the inside at this point. But what you can also do, well, at this point, there's a couple ways you can do it. But now what I'm going to do is I'm going to finally multiply that 3 over n into each term. So if I do that, hopefully it's clear that this will become 12 right here, this first term, because the n and the n cancel. And then we're going to get what? We're going to get plus 9 for this next one, because 3n times 3 is 9n over n is 9. And then, and actually, I guess I should have combined this beforehand. That's 7n, so it's actually going to be 21n. Yeah, if I want to do that, 12n plus 9n, 21n, and then here plus 3 times 3 over n. That's actually going to be plus 9 over n, right? And then what are we going to have? We're going to have minus. So let's think about this. We're going to have minus 3 times 3 is 9 times 2. So what's 9 times 2? That's going to be basically 18. So minus 18. Well, I guess we'll have over 2, right? So this 2, and actually, let me just multiply. I'll just multiply this in first, and then we'll deal with that later. Actually, 9 over 2n squared. So 9 over 2n squared, right? If I just multiply the 3n times that negative 3 over 2n, negative 9 over 2n squared. Then we have 2n squared plus 3n plus 1. I'll just leave it like that. And then the limit of that whole thing as n goes to infinity. So now what? Now, again, it's probably best to multiply this through. So here's the thing. There's a couple. I'll say a couple things. So first off, for this first term, the n squareds are going to cancel out, and we'll be left with just a number. That's fine. So we'll talk about that. And then the next thing to notice is that the I guess how should I word this? Or sorry, I wrote that wrong. This should not be 21n. This should be, sorry, these n should not be here. So this should be well they are up there, but when we distribute it in here, it'll just be 21. There we go. Not 21n. And now here, as we multiply these, so you can actually do the multiplication, or if you know where we're going, you can like simplify it a little bit. So where are we going? N is going to go to infinity. That means, so first off, if n is in the numerator anywhere, the whole thing is going to blow up to infinity, right? Because infinity, like if the numerator goes to infinity, the whole thing blows up. But what we're taking advantage of is n being in the denominator. So if n is in the denominator and n goes to infinity, that whole thing goes to 0, right? Because what's 9 divided by 1,000? Small number. What's 9 divided by a trillion? A way smaller number. It's like it approaches 0 in the limit. It'll never hit 0, but it gets closer to 0 as n grows. So if you look at it, you can kind of tell that these two, once I actually multiply in the n squared, or the division by n squared, those will have n in the denominator, right? Because n over n squared is going to be 1 over n. 1 over n squared is going to be 1 over n squared. It doesn't really matter whether it's 1 over n or 1 over n squared. The thing that matters is they're in the denominator. And as n goes to infinity, those will go to 0. So if you already noticed that, you can kind of just cancel those out right now. Otherwise, I'll just multiply it all the way through, like just to do it. But you can save yourself a little bit of work if you notice that. So here, hopefully this is clear. That'll just be minus 9 if I distribute that in first. And then the next one, that'll be what? Minus 27 over 2n, right? And then minus 9 over 2n squared, right? And we still have 21 plus 9 over n. And then let's just take the limit of this whole thing as n goes to infinity. Because remember, that's the whole goal. Like this initial expression was like, oh, we have a bunch of rectangles, we have n rectangles, and we're taking the limit as n goes to infinity. Everything we did, all that crazy stuff we did above, was to get a formula for the area under the curve if we have n rectangles, and we're using the right Riemann sum. And now here, if we just take the limit of this, again, anything with n in the denominator is going to go to 0, right? As n goes to infinity, those go to 0. So we're going to be left with 21 over 9. What's that? Well, that's just 12. What did we say that the answer was at the beginning of our live earlier today? We said it doesn't really matter whether we do the left Riemann sum, the right Riemann sum, or the midpoint. We're clearly getting closer to 12 no matter how we slice it. As we let n go to infinity, here we just proved it. This is the exact area under the curve. Voila. That is called everything we just did today. This is the limit definition of the integral. And you can see how long it took to actually do it. But the big benefit is we found the exact area under the curve, not an approximation. It made us want to pull our hair out when we did it, but it is doable. It is possible as long as you know how to work with summations and you know how to simplify certain formulas. You can do that. Now here, this is a little preview for what we'll talk about probably tomorrow, I think. There's a faster way to do this with something called, I've used the word, I think, something called the integral. And so and this is, again, Desmos understands this, but if I just do -1 to 2, and then I do the function that we're talking about, so 5 minus x squared dx, you can see it goes to the answer immediately. Now, this is kind of like, this is what we just did, but it does it in a much more efficient way, and we'll talk like with a lot less work. You can basically do all the work we just did. Let's count how many lines there are just to make ourselves cry. So 1, 2, 3, 4, 5, 6, 7. All right, I'm bored already. So it's like there's like 20 lines, like 15 or 20 lines. Very painful problem. You can do it in like 2 lines or 3 lines once you know this. There's a special trick you have to kind of get used to. But the good news is you already kind of know how to do it. You just have to do something you already know in reverse. And we'll talk about that tomorrow. But this is like a 10 or 20 times or 10 times easier way, let's say, than what we just did to do the same thing to find the exact area under the curve. That's called the integral, and that's what we'll talk about tomorrow. So hopefully that makes sense. Any questions on that from anybody in the chat? If not, then yeah, thanks for coming today. Feel free to just drop any questions if you have them in Skool, and I'll get to them. Oh yeah, I'll get to them as soon as I see them. Thank you. Catch you guys later.